Welcome back to Topic 5 for Algebra 2, Solve and Graph Absolute Value Inequalities. In this video, we're going to learn about what is an absolute value inequality and what it looks like on a graph, as well as solve some examples. So before we get into absolute value inequalities, let's first remember what an absolute value equation is. Let's recall that the absolute value of x equals 3 means that x is 3 units from 0. So think about distance on a number line. If we think to the absolute value of x is less than 3, this means that x is closer than or less than 3 units from 0. So we can write this as a compound inequality, where x is less than 3 and x is greater than negative 3. We can also write this in a compact form because we're dealing with an and compound inequality, where negative 3 is less than x, which is less than 3. Let's look at this on the number line. So if we have 0, 3, and negative 3, we'll just have it be open circles because we're dealing with strictly less than. Now here we're going to shade in the center, because in our compact compound inequality, we see that x is lying in between negative 3 and 3. So if we think back to closer than 3 units from 0, if we start at 0, where our possible value of x is, it's going to be a little bit less than 3 units. It's not going to be exactly 3 units. Same if we think on the positive side versus the negative side. Now on the other hand, if we have the absolute value of x is greater than 3, this means that x is further than or greater than 3 units from 0. We can write this as the compound inequality. X is less than negative 3, or x is greater than positive 3. Now again, if we think about this on our number line, let's just have our open circles here. Now I'm going to shade, since x is less than negative 3, I'm going to shade to the left here. If x is greater than positive 3, I'm going to shade to the right here. Again, thinking back to further than 3 units. So if we start at 0, we are further than 3 units to our potential x value. And this goes the same for both sides. So a helpful key that I like to do is whenever we have the absolute value of x is less than or equal to, this is a center segment for where you would shade. And this represents an and absolute value inequality. On the other hand, if we have the absolute value of x is greater than or equal to, we're going to shade in opposite directions, so we have two tails. This is for an or absolute value inequality. A trick that I personally like to use is I think of less than and less than. And if we have greater than, greater than, greater than, that helps me, just kind of that little phonetic. Let's move into some examples. So just like when we were dealing with absolute value equations, we want to isolate our absolute value. It is at that point that we can determine where we're shading. So once we isolate our absolute value, now we can look at our inequality here. So if we go back to our key, we have a greater than or equal to. Greater than or equal to is, we're going to shade tails because it's an or. So I'm going to circle tails and or. Now at the same point that we would have for an absolute value equation, we would split. So I'm going to split here. We have x minus 4 is greater than or equal to 8. And x minus 4 is less than or equal to negative 8. So just like with absolute value equations, we change the sign with one of our equations after we split. With absolute value inequalities, we have to change the sign of our number and the inequality sign. So you have two things to think about with absolute value inequalities. Now we're going to go about and solve this just how we would normally with an absolute value, with a regular inequality. So we can add 4 to both sides. Feel free to do this simultaneously with the other inequality as well. Negative 4 plus 4 adds to 0, so we're just left with x on the left-hand side. X is greater than or equal to 12, and x is less than or equal to negative 4. So now we can mark this on our graph. Since it is greater than or equal to and less than or equal to, we're going to have closed circles. And because we already did this in the beginning, we know it's an or, and we're going to have two tails for shading. We can also look at our inequalities. Greater than or equal to 12, so we're going to shade to the right. Less than or equal to negative 4, so we're going to shade to the left. Moving on to number 2, here we have the absolute value of 1/4 y plus 5 is less than 11. So again, we do not need to isolate our absolute value because it is already alone. We do not have any other stragglers. So we can just look at our inequality right here. Our inequality right here is less than, so we have an and. I'm going to shade in the center. Now we can split. So we have 1/4 y plus 5 is less than 11, and 1/4 y plus 5 is greater than negative 11. Now we're going to go about and solve our two-step inequality, subtracting 5 from both sides. Positive 5 minus 5 adds to 0, so we're just left with 1/4 y is less than 6, and 1/4 y is greater than negative 16. Now here we have 1/4 y. I like to see this because we have a fraction here, so that represents division. So instead of dividing both sides by 1/4, we can multiply both sides by the reciprocal, which is 4/1. On the left-hand side, it reduces to 1y, or just y. And on the right-hand side, we have 6 times 4/1, which is 24, and negative 16 times 4, which is negative 64. Now, because this is an and, we can write this in the compact format, the smooshed format, and get, I changed the inequality here. Y is greater than negative 64. I apologize. That's why it's always good to double check your work. So we have negative 64 is less than y, which is less than 24. We can put this on our graph now. We have open circles for both because it is strictly less than or strictly greater than. And it already tells us where we're going to shade, so we're going to shade in the center. We can also look at our compact format. Y lies between negative 64 and positive 24, so that's where we're going to shade. Moving on to example number 3, we have negative 2 times the absolute value of 3 plus x, plus 5 is less than 11. So here we have some stragglers. We need to first isolate our absolute value, so get it alone. Treat it just like a variable, this absolute value. So what we're first going to do is subtract 5. from both sides and get negative 2 times the absolute value of 3 plus x is less than 6. Then, since this is 2 times this quantity, this absolute value, we're going to apply the inverse, which is division, and divide both sides by negative 2. On the left-hand side, that reduces to 1 times that absolute value, or just the absolute value of 3 plus x. And on the right-hand side, we have 6 divided by negative 2, which gives us negative 3. Now here, because we are dividing by a negative number, we have to flip our inequality sign. So think back to Algebra 2 topic 3. When we multiply or divide by a negative number, our inequality sign must flip. Once we have our quantity isolated here, our absolute value isolated, now we can determine if we're going to have center or tails for shading, and if it's an and or an or inequality. So if we look at our inequality here, we have a greater than, so we know that it's a greater, and we're going to have tails for shading. At this point, now we can split. So we have 3 plus x is greater than negative 3, or 3 plus x is less than positive 3. So again, our sign, our inequality sign and our number sign change. Since this is a positive 3, now we're going to isolate our x by subtracting 3 from both sides. And we get x is greater than negative 6, or x is less than 0. So again, this is an or, based on what we chose up here from that inequality, the greater than sign. So I'm going to graph these two inequalities first separately, in hopes that that can help us with graphing the complete inequality together. If something is greater than negative 6, we're going to have an open circle and shade to the right. If something is less than 0, we have an open circle and shade to the left. So in this problem, we need to think of numbers that are either greater than negative 6 or less than 0. So numbers that are greater than negative 6, we could have negative 5, 10, 250, etc. Numbers that are less than 0 could be negative 1, negative 10, negative 1,000, etc., etc. However, if we need to decide something that are either greater than negative 6 or less than 0, we have infinite possibilities. There are infinitely many numbers that are bigger than negative 6 or less than 0. Because this is an or inequality, it is less restrictive. It is all-inclusive, rainbows and butterflies, everyone can sit with us. So on our graph, we can mark 0 and negative 6 with open circles, but actually all of the values that we're going to shade cover the entire number line. So notice here how my circles are actually filled in. That's because 0 is not less than 0, but 0 is actually greater than negative 6, so it fits. And same with the other example. Negative 6 is not greater than negative 6, but it's certainly less than 0. So our solution here is all real numbers, the entire number line here. Moving on to our fourth and final example. Here we have the absolute value of 5x minus 13 plus 7 is less than or equal to 6. So we still need to isolate this absolute value. So we're going to subtract 7 on both sides first. And we have the absolute value of 5x minus 13 is less than or equal to negative 1. At this point, since that absolute value is isolated, we can now determine if this is going to be an and or an or. Since it's less than or equal to, we know that it's going to be a center and. Now we can split. So we have 5x minus 13 is less than or equal to -1. And we have 5x minus 13 is greater than or equal to, I should make that a different color, greater than or equal to +1. So notice here also when I branch, the absolute value signs disappear. So there's no need for them anymore. Now let's go about and solve. So we're going to add 13 to both sides. -13 plus 13 are inverses, they add to 0. We have 5x is less than or equal to 12. 5x is greater than or equal to 14. Divide everything by 5. Since 5 and x are tied together with multiplication, inverse is division. So we get x is less than or equal to 12/5, and x is greater than or equal to 14/5. If we want to write it in the compound, x is bigger than 14/5 and x is less than or equal to 12/5. We want to think about this as, is there actually a number that is smaller than 12/5 and bigger than 14/5? Now, if the fractions are confusing you, let's ignore them for a second. Is there a number, I'm going to write this on the side here. Is there a number that is less than or equal to 12/5 and greater than or equal to 14/5? So again, if we take away that denominator just to kind of minimize confusion, is there a number that's smaller than 12 and bigger than 14? No, there's no possible number that is smaller than 12 and bigger than 14. So same thing with 12/5 and 14/5. There is no possible number. Nope. So our answer is no solution. And for the graph for this, you don't even need to mark it up. You don't need to make any notes on the graph. So sometimes we can get a solution on the graph with tails, with a center part shaded. Sometimes we might have the entire number line shaded, so it's all real numbers. And sometimes our graph might have nothing on it. It might have no solution. That was topic 5 for Algebra 2, solve absolute value inequalities. Thank you for watching.